A single replacement reaction is one of the oldest redox reactions. It's a redox reaction where we have an ion in solution that becomes reduced and we have an oxidation of some metallic element. In this example, we have a solution of copper 2 sulfate. That means that there's copper ions swimming around in solution along with sulfate ions, which are really just spectator ions. We can imagine what would happen if we dipped some metal zinc into our copper 2 sulfate solution. The zinc will go from a 0 oxidation state up to a +2 oxidation state. Therefore, our zinc was oxidized, going from a 0 to a +2. Our copper will actually crash out on the surface and go from a +2 oxidation state in the solution down to a 0 oxidation state when it's elemental copper. On the surface of the zinc, this black tarnish is actually copper if we allowed it to dry. The copper crashed out on the surface. We plated out that metal. Remaining in the solution now are leftover zinc ions from the metal zinc becoming oxidized. There's still some copper ions swimming around in here, along with some sulfate anions. But now there's less copper ions in solution than there were initially, because some of it was reduced to metallic copper. This next picture gives us an idea of what's happening at the subatomic level on the surface of the zinc and to the ions surrounding the zinc. When we dip that solid zinc into our solution of copper, the zinc gives up 2 electrons and it transfers them to the copper ion. The copper ion accepts those 2 electrons to become reduced to elemental copper. When zinc gives up those 2 electrons, it now has become a zinc ion. The zinc ion is aqueous and will be dissolved in the water. This back and forth between zinc giving up electrons and copper accepting electrons is what causes our redox reaction to occur. You can't have oxidation without reduction. Something must lose electrons and something must gain electrons. The reason this reaction happens in the first place is because our zinc is going to be able to replace our copper. The zinc is more active, we say, meaning it's more easily oxidized to an ion. Copper is less active than zinc, therefore it wants to be reduced more. We can predict if a single replacement reaction will occur by using something called the activity series for metals. The activity series lists our metals based upon how active they are or how easily oxidized they are. A metal in the activity series will reduce the ion of any metal below it, which will lead to a single replacement reaction. As we go from the bottom all the way to the top on the left-hand side, our metals are increasing in their ease of oxidation. That means that lithium is the most easily oxidized to the lithium plus ion, and gold at the bottom is the least easily oxidized to the gold 3 plus ion. On the opposite side, looking at the ions as we go from top to bottom, this is showing us the increasing ease of reduction of the ion. That means that lithium ion does not want to be reduced back to solid lithium. It would much rather be oxidized. At the bottom, our gold 3 plus ion really would like to be reduced back to gold. It's got the greatest ease of reduction. So we have to consider 2 things. We have to consider the metal on the left-hand side of the arrow, and we have to consider the ion on the right-hand side of the arrow. These 2 things will tell us if a single replacement reaction will take place. For example, on the last slide, we saw the reaction between zinc and copper 2 plus ions in solution, and that formed solid copper, and it made the zinc oxidize into zinc 2 plus ions in solution. If we locate our zinc and our copper ions on this activity series, we can predict why that reaction took place. Zinc on the left-hand side as a metallic element is right here, and copper ion is over here on the right-hand side. Notice that the zinc is higher on the activity series on the left-hand side than the copper ion is on the right-hand side. If that's the case, a single replacement reaction will take place because the metal is more active, the zinc metal is more active than the copper is. Zinc wants to be oxidized to the 2+ charge, and copper wants to be reduced back to elemental copper. If the metal on the left is higher than the ion on the right, then a single replacement reaction will take place. Now let's imagine we have another reaction. Let's pretend we have a reaction and we're wondering if it'll happen between zinc and strontium. Will this be able to lead to a single replacement reaction where zinc becomes oxidized and strontium becomes reduced? Zinc as a metal is over on the left-hand side, and strontium as an ion is over here on the right-hand side. Notice that the ion is higher on the right than the metal is on the left. In this case, no single replacement reaction will occur because the strontium is more active than the zinc, and it's already in its oxidized form. Therefore, the zinc cannot become oxidized and reduce the strontium. This is how we read the activity series to predict our reactions. You will be given this activity series on quizzes and exams, so just make sure you practice using it and know how to tell if something can be oxidized by something else. Using your activity series handout, we want to determine if the following single replacement reactions will occur. For the first one, we have solid copper and we have aqueous silver ions. We want to know, is copper more active than silver? Can copper get oxidized and cause silver to be reduced? When we look at the activity series, the solid metal copper on the left is going to be higher than the silver ion is on the right-hand side of the arrow. This means that our copper is more active or more easily oxidized. That tells us that yes, a single replacement reaction will take place where the copper becomes oxidized to copper 2+ and the silver becomes reduced to elemental metallic silver. In our next example, we have solid gold reacting with silver ions in solution. In this case, when we find our gold on the left-hand side and we find our aqueous silver ions on the right-hand side, the gold is lower on the activity series than the silver ions. This means that no single replacement reaction can take place. So really this would be no reaction and these products would not be formed because silver is more active than gold. And it's already in its oxidized form. Therefore, gold cannot take its place in solution. Predict if the following redox reactions will occur. In our first one, we have hydrogen ions and platinum solid. Can platinum take the place of hydrogen in solution and cause hydrogen ions to be reduced to H2 gas while the platinum gets oxidized? So we want to locate our platinum solid and our hydrogen ions on our activity chart. The metal platinum is lower on the left-hand side of the arrow than the hydrogen ion is on the right. That means hydrogen is more active. And since hydrogen is already oxidized, no reaction will occur. Platinum is not active enough to reduce hydrogen. For the reaction of calcium ions with magnesium, can the magnesium become oxidized and cause our calcium to get reduced to elemental calcium? The magnesium is also below the calcium ion. Therefore, magnesium is not active enough to cause calcium to be reduced. No reaction. And on the last one, can zinc replace mercury in solution and cause the mercury to get reduced to liquid mercury while zinc become oxidized? If we look, zinc on the left-hand side of the arrow is higher up than mercury ion is on the right. Therefore, our zinc is more active than mercury. Therefore, it will become oxidized to zinc 2+, and the mercury will become reduced. Mercury will have a 0 oxidation state, and zinc will have a +2 oxidation state. So yes, this reaction will happen. At the beginning of Chapter 4, we balanced chemical equations by looking at the number and types of atoms on the reactant side and on the product side and making them the same by adjusting the stoichiometric coefficients out front. But when balancing redox reactions, it's a little bit more involved because now the charges of our species are changing as well, whereas before they were not. By following something called the ion-electron method, this outlines a series of steps that we can follow in order to balance any redox reaction. First, we'll divide our reaction into two separate half reactions, one for oxidation, one for reduction. Then we'll balance each of the half reactions separately. First, we'll balance them by mass by looking at the number and types of atoms present, but then we'll balance them by charge. We balance charge by using electrons. Electrons have a negative charge. Those will be symbolized by writing E-. We have to make sure the electrons gained from one half reaction equal the electrons lost from another half reaction. So when we add them together, we end up canceling out our electrons. We should have no electrons in the overall equation. After we cancel our electrons, then we can add our two half reactions together to get our overall balanced redox equation. Let's try a few examples. Predict the outcome of the following reactions. If no reaction occurs, write NR. If a reaction occurs, write a balanced chemical equation. So the first thing we have to do is use the activity series to determine if a reaction will occur in the first place. Can manganese replace iron 2+ in solution? Is manganese more active? And if we look at our activity series, we'll see that the solid manganese is higher on the left than the iron ion is on the right-hand side of the arrow. Therefore, yes, a single replacement reaction can take place. When it does take place, we will form manganese 2+ ion. That'll be an aqueous ion in solution. And the iron will crash out as solid iron and be reduced. Now, it might look like the reaction is balanced, but we have to check. So the first thing we need to do is break our equation up into two half reactions, one for oxidation and one for reduction. The manganese started at a 0 oxidation state on the left-hand side, and it went to a +2 oxidation state. That means our oxidation half reaction is for manganese. Manganese going to manganese 2+. Our iron started at a +2 oxidation state, and it went down to a 0 oxidation state. That's a reduction. Our reduction half reaction will be for the iron 2+ ion. First, we need to balance our reactions by mass. That means looking at it and determining the number of atoms. For our oxidation half reaction, we have 1 manganese on the left, and we have 1 manganese on the right. For our iron, we have 1 iron on the left, and we have 1 iron on the right. It doesn't matter that some are in ion form. Next, we have to balance the charge. The charge is going to be 0 on the left-hand side for our manganese half reaction, and we have 1 manganese 2+ ion. So the total charge on the right is +2. How can we make those two charges the same? We have to add electrons. We're going to need to add 2 electrons to the right-hand side of the oxidation reaction in order to make our +2 charge equal to 0. For our iron half reaction, our iron 2+ on the left has a +2 charge, and our iron on the right has a 0 charge. We need to make our charges the same, so we're going to add 2 electrons to the left-hand side to bring our +2 charge down to 0. We should always be adding electrons to opposite sides of our half reactions. They should never be added to the same side, since oxidation always occurs with reduction. Next, we're going to add our two half reactions together to get our overall equation. Our 2 electrons cancel. They're kind of like spectator ions. We have the same amount, and they're on opposite sides of the arrow. And what we're left with is our balanced equation. Manganese plus iron 2+ going to manganese 2+ plus elemental iron. So in this example, it just happens that our coefficients out front were all 1 to 1 to 1 to 1. That happened because our manganese became a positive 2 ion and our iron was also a positive 2 ion. That won't always be the case where our charges are the same, but in this example it was. So this represents our overall balanced net ionic equation. Let's try another example where we have different charges. Can magnesium replace silver in solution, where magnesium becomes oxidized and silver becomes reduced? Magnesium metal is higher on the activity series than silver is, so yes, this reaction will take place. And when it does, we will form magnesium ions that will be aqueous, and our silver will be reduced down to solid silver. Now that we predicted the products and we determined that the reaction will occur, let's determine our two half reactions. Magnesium on the left has a 0 oxidation state, and on the right it has a +2 oxidation state. So therefore magnesium was oxidized. Our magnesium went from a 0 oxidation state to a +2. Our silver started with a +1 oxidation state and it went down to a 0 oxidation state. So our silver is our reduction half reaction, silver plus going down to silver. Balancing by mass, we have 1 magnesium and 1 magnesium. We have 1 silver and 1 silver. And then balancing by charge, we have to consider the number of electrons. Our charge on the left-hand side of our oxidation half reaction is 0. It's +2 on the right. So we're going to need to add 2 electrons, each which have a negative charge, to the right-hand side. Electrons are a product when you have oxidation because they're lost. On our reduction half reaction, silver has a +1 charge on the right, and it has no charge, or it has a +1 charge on the left and it has no charge on the right. Therefore, to make our +1 0, we're going to need to add 1 electron to the left-hand side of our reduction half reaction. If we were to stop and add up our two half reactions now, our electrons wouldn't cancel out, and we can't have any electrons in our overall balanced equation. So sometimes we need to multiply one of our half reactions or both of our half reactions through by a number. In this case, if we multiply our bottom half reaction through by 2 and multiply everything in there by 2, that will make our electrons the same. That will give us 2 Ag plus 2 electrons, forming 2 silver. Now we can add together our two half reactions. Let's rewrite our first one on top of the second one. Magnesium going to magnesium 2 plus our 2 electrons. Here we can see that our electrons are going to cancel. The 2 electrons on the left with the 2 electrons on the right. And what we're left with then is magnesium plus 2 silver ions, forming a magnesium ion plus 2 Ag. Those are going to be our coefficients for our overall balanced equation. We can plug them in at the top. 1 magnesium, 2 silver, 1 magnesium ion, 2 silver on the right. The only way we could figure those out was by going through the ion-electron method and determining the changes in the charges for our overall balanced net ionic equation. In this example, we have cadmium metal reacting with aqueous zinc ions. Can cadmium become oxidized and replace zinc in solution while zinc becomes reduced? If we find these on the activity series, we'll see that zinc is higher up, meaning our zinc is more active than our cadmium is. If this is the case, then we don't have to do any of the work because this is no reaction that will take place, and that's all we have to write. No reaction because our zinc is already oxidized and it's more reactive than the cadmium. In our last example, we have chromium solid reacting with aqueous tin ions. Chromium is higher on the activity series than tin, therefore a single replacement reaction can take place and chromium will replace tin in solution. When chromium becomes oxidized, according to the activity series, it forms a 3+ ion. And when tin becomes reduced, it'll be reduced down to solid tin. Determining the changes in our oxidation numbers for our half reactions. Our oxidation half reaction will be that for chromium going to chromium 3 plus ion. And our reduction half reaction will be that for tin 2 plus going to elemental tin. Everything is balanced by mass in both of our half reactions. We have 1 of all of our species. Balancing by charge, our oxidation half reaction, we have 0 charge on the left-hand side and plus 3 on the right. So we need to add 3 electrons to the right-hand side of the equation. For our reduction half reaction, tin has a plus 2 charge on the left and no charge on the right since it's a free element. So we need to add 2 electrons to the left-hand side of the half reaction. Our next step is to make our electrons gained equal our electrons lost. So we're going to need to multiply our top reaction through by 2 and our bottom reaction through by 3. In that case, it'll give us 6 electrons for both of our half reactions, and they'll cancel when we add them together. Therefore, if we rewrite our top oxidation reaction, we'll get 2 chromium going to 2 Cr3 plus we'll get 6 electrons. For our reduction half reaction, we'll get 3 tin 2 plus 6 electrons going to 3 tin. Now if we're to add our half reactions together, our electrons are on opposite sides of the arrows and they're the same coefficient. Therefore, our 6 electrons cancel with one another. Our overall balanced equation will be 2Cr plus 3SN2 plus going to 2Cr3 plus 3SN. Those are going to be our coefficients that we get to plug in. 2, 3, 2, 3 for our overall balanced redox reaction. In the last few examples we did of balancing redox reactions, we were assuming that those reactions were carried out in a neutral solution of just water. But many redox reactions are also carried out in acidic or basic solutions. This can dictate the products that are formed. When we have an acidic or basic solution, the hydrogen ion, the hydroxide ion, and water play an important role in the overall balanced equation. The products can change depending upon the pH of the solution. An acid has a pH of less than 7, while a base has a pH of greater than 7. For example, in an acidic solution, the permanganate ion is reduced to the Mn2 plus ion. We could determine this by figuring out the oxidation state of manganate. 2 minus for the oxygen, 8 minus total since there's 4 of them, and it has to add to a -1, so manganese must have been a +7. It gets reduced down to a +2. Whereas in basic solution or a neutral solution, that same permanganate ion turns into manganese 4 oxide. This is a solid precipitate and a totally different product than our manganese 2 plus ion. So the pH of the solution determines the products and the species in the overall balanced equation. The rules that we'll follow for balancing an acidic solution will be first divide the equation into their 2 half reactions, oxidation and reduction. When we balance by mass, we'll start by balancing atoms other than hydrogen and oxygen. Next, we'll balance oxygen by adding a certain number of H2O molecules that are needed. Then we'll balance our hydrogens by adding hydrogen ions, or a proton. Next, we'll balance our charge, just like we did originally, by adding electrons to one side of our half reaction. Then we'll make our electrons gained equal our electrons lost, and add those 2 half reactions together. Finally, we can cancel anything that's the same on both sides of our half reactions. Balance the following redox equation in acidic solution. We have to be told if we're balancing an acidic or basic solution in the problem. First, let's break it up into 2 half reactions. Fe2 plus going to Fe3 plus will be one of our half reactions. since iron is only present by itself. Our other half reaction will be the dichromate ion, Cr2O7 2-, going to chromium 3+ ion. In our first half reaction, we want to balance everything other than hydrogen and oxygen. And there is no hydrogen or oxygen present, we just have iron. We have one iron on the left and one iron on the right-hand side. So everything's balanced by mass in our first half reaction. For our second half reaction, we have 2 chromiums on the left-hand side, and right now we only have 1 chromium on the right-hand side. So we're going to need to put a coefficient of 2 out in front of our Cr3+. Next, we balance our oxygens. We have 7 oxygens on the left-hand side and none on the right. We balance oxygens by adding H2O. So we're going to add +7 H2O. By introducing our 7 water molecules, we also included 14 hydrogens. To balance our hydrogens, we add H+ ions. So we're going to need to add 14 hydrogen ions to the left-hand side to balance our hydrogens now. All of our atoms are balanced by mass at this point. Now we're going to balance by charge. In our first half reaction, we have a total of a +2 charge on the left, and we have a +3 charge on the right-hand side. We have to make our 2 charges the same by adding electrons. We can bring our +3 charge down to a +2 by adding 1 electron to the right-hand side. For our second half reaction, we want to take a tally of the total charges. The total charge on the left-hand side, we have 14 + 1 charges from our hydrogen ions, and we have 1 -2 charge from our dichromate ion. So our total charge is going to be +12 on the left-hand side. On the right-hand side, we have water, which is neutral, so it has no charge, and we have 2 chromium ions, each that have a 3+ charge. So our total charge on the right-hand side is +6. We need to make our charges match on the left and the right-hand side, so we're going to have to bring our +12 down to a +6 by adding 6 electrons to the left-hand side. Now we've balanced by mass and we've balanced by charged, but our electrons gained don't equal our electrons lost yet. We're going to need to multiply the top half reaction through by 6 in order to make our electrons the same. When we do that, we'll get 6 Fe2+ going to 6 Fe3+ plus 6 electrons. Now we're going to be able to add up our 2 half reactions, and everything that we need to cancel should cancel. Our 6 electrons are on the right-hand side of our top half reaction, so that was an oxidation of iron, and they're a reactant on our left-hand side of our bottom half reaction. So our bottom half reaction was a reduction of the chromium. So rewriting our second half reaction, we can more easily see where we're going to add together. Our electrons will cancel, and then everything gets added on the left-hand side of the arrow together, and everything on the right-hand side of the arrows get added together. So our final equation will be 6Fe2+ plus our dichromate ion, Cr2O7 2-, plus 14 hydrogen ions. And then going to our product side, we'll have 6Fe3+ plus 2 Cr3+ plus our 7 water molecules. This is our overall balanced equation in acidic solution. Whenever you balance an acidic solution, you should usually have hydrogen ion or proton. That tells us it's an acid. And there will also usually be some water to look for on one side of the equation. Let's try another example in acidic solution. First, we have to break our overall redox reaction into our 2 half reactions. Our permanganate ion MnO4 minus will be going to Mn2 plus, and our H2SO3 will be going to the sulfate ion SO42 minus. Starting with our top half reaction, we have one manganese on the left and one manganese on the right, so that's balanced. Now moving to oxygen, we have 4 oxygens on the left and none on the right, so we're going to need to balance using water. We'll need 4 H2O. By introducing 4 oxygens, we've also introduced 8 hydrogens, so we're going to need to add 8 H plus on the left. It's important that you remember to write H plus and not just H, because hydrogen is balanced by using the hydrogen ion, which will be necessary when calculating our charges. Everything's balanced by mass in the top half reaction. For our bottom half reaction, we would check sulfur first. We have 1 sulfur on the left and 1 sulfur on the right, and then move on to oxygen. We have 4 oxygens on the right and only 3 on the left, so we're going to need to add 1 water molecule to balance our oxygens. And now we have a total of 4 hydrogens on the left and none on the right, so we're going to add 4 hydrogen ions to our right-hand side. And everything's balanced by mass here now. For charges, we have to figure out what the total charge on each side is. We have 8 hydrogen ions and 1 permanganate that has a negative charge, so our total charge on the left-hand side is +7. On the right-hand side, we have 4 waters, which are neutral, and we have 1 Mn, which is a 2 plus charge. So we have a +2 for our total charge on the right-hand side. We can make our +7 come down to a +2 by adding 5 electrons to the left-hand side of the top half reaction. For our bottom half reaction, water and sulfurous acid both are neutral, so the left-hand side has no charge, 0. And on the right-hand side, we have 4 hydrogen ions and we have 1 sulfate, which is a -2. So our total charge is going to be +2. We can make our +2 come down to a 0 by adding 2 electrons to the right-hand side. Next, we have to make our electrons gained equal our electrons lost. That means we're going to multiply the top equation through by 2 and the bottom equation through by 5 in order to get our electrons to be the same. Rewriting our top equation multiplied through by 2 gives us 16 hydrogen ions plus 2 permanganate plus 10 electrons. And on our product side, we'll have 2 Mn2 plus 8 H2O. For our second half reaction, we're going to have 5 H2O plus 5 H2SO3. Products, 5 sulfate ions plus 20 hydrogen ions plus 10 electrons. Now when we go to add our two half reactions together, there's a few things we get to cancel. First and foremost, we have to be able to cancel our electrons. And we have 10 electrons on the left-hand side of the arrow and on the right-hand side of the arrow. So those go away. But we also have water and hydrogen ion. On the right-hand side of the arrow, there's 8 water molecules. And on the left-hand side, there's 5 water molecules. All 5 of the water molecules will cancel with some of the 8. We'll end up with 8 minus 5, or 3 H2O left over on the right-hand side, where the number was greater. In terms of our hydrogen ions, we had 16 hydrogen ions on the left, 20 hydrogen ions on the right. All 16 will cancel, and we'll be left with 20 minus 16, or 4 hydrogen ions left over on the right-hand side as well. So now when we add everything on the left-hand side and the right-hand side of the arrows, we've already simplified our equation. What we'll be left with is 5H2SO3 plus 2 MnO4 minus, forming 2 Mn2 plus 5 sulfate SO42 minus plus 5 H2O plus 4 hydrogen ions, 4H plus. This would be our overall balanced equation in acidic solution. Balance the following redox reaction in acidic solution. Breaking this up into our two half reactions, we're going to have the nitrate anion, NO3 minus, forming nitrogen monoxide, NO, and our second half reaction is copper forming copper 2 plus ions. Looking at our first half reaction, our nitrogens are already balanced, so we can move on to our oxygen. We have 3 oxygens on the left and 1 oxygen on the right, so we're going to need to add plus 2 H2O in order to get 2 more oxygen atoms. Now we've added 4 hydrogens to the right-hand side, so we're going to need to come over to the left-hand side and add 4 H plus in order to balance our hydrogens. Looking at the bottom half reaction with copper, our copper is already balanced. We have 1 copper on the left, 1 copper on the right, and there's nothing else for us to balance there. Now we can balance our charges. On the left-hand side of our top half reaction, we have 4 plus 1 charges and 1 minus 1 charge. So our total charge is plus 3. And on the right-hand side, water and nitrogen monoxide are both neutral. Neither have a charge. So the total charge is 0 on the right. We're going to need to add 3 electrons to the left-hand side of our half reaction to make our plus 3 charge become the same as 0. In our bottom half reaction with copper, our copper has no charge, so it's a 0, and our copper 2 ion has a plus 2 charge. So we will need to add 2 electrons to the right-hand side to bring our plus 2 charge down to 0. Next, we'll make our electrons gained equal our electrons lost by multiplying our top reaction through by 2 and our bottom reaction through by 3, giving us 6 electrons in each. Our first reaction will be 8 hydrogen ions plus 2 nitrate ions plus 6 electrons, and on the product side we'll have 2 NO plus 4 water molecules. For our bottom half reaction, we'll get 3 copper going to 3 copper 2 plus 6 electrons. Now our electrons gained equal our electrons lost for both of our half reactions, and we can cancel out our electrons. They're on opposite sides of the arrows and they're the same. Adding together our two half reactions gives us 8H plus 2 NO3 minus plus 3 Cu on our reactant side, and on our product side we have 2 NO plus 4 H2O plus 3 Cu2 plus. This will give us our overall balanced equation in acidic solution. If we need to balance in basic solution, there's a few additional steps that we're going to have to tack on to the end of the steps we were just following for balancing in acidic solution. We would follow everything the same up until the very end. Then after, we would add to both sides of the equation the same number of hydroxide ions as there are hydrogen ions present. We shouldn't have any hydrogen ions present in a basic solution, but we should have hydroxide and water. We can combine those hydrogen ions with the hydroxide ions to form more water molecules, and then we want to make sure to cancel out anything that is the same on the left and the right hand side. Usually we will have some water molecules that will cancel out. In this example, we'll practice balancing in basic solution now. Just like the acidic solution, we have to be told what the pH is. So now we know our pH is greater than 7. First, we want to break our redox reaction up into our two half reactions. So we're going to have ClO minus going to Cl minus, and we're going to have CrOH4 negative charge going to CrO4 2 minus. In our first half reaction, we have 1 chlorine on the left and 1 chlorine on the right. We have 1 oxygen on the left and none on the right, So we're going to add one H2O molecule to the right-hand side. And now we have 2 hydrogens, so we're going to need to come over to the left and add plus 2 hydrogen ions. Now all of our hydrogens, oxygens, and chlorine is balanced. In our bottom half reaction, we have 1 chromium on the left and 1 chromium on the right. We have 4 oxygens on the left and 4 oxygens on the right as well, but our hydrogens are not balanced. We have 4 hydrogens on the left and none on the right, so we're going to add plus 4H plus to the right-hand side. Next, we'll take a tally of our charges. On our top half reaction, we have a total of a plus 1 charge, since we have 2 hydrogens and 1 hypochlorite ion, which is a -1. And on the right-hand side, we have a chlorine, which is -1, and water, which is neutral. So we have a -1 total charge on the left. We can bring our +1 down to a -1 by adding 2 electrons to the left-hand side. In our bottom half reaction, on the left-hand side, we have only 1 species present, and it has a -1 charge. On the right-hand side, we have our dichromate ion, and we have 4 hydrogen ions, so we're going to have left over a +2 charge. We can make our +2 a -1 by adding 3 electrons to the right-hand side. The top one would represent our reduction half reaction, where electrons are a reactant, and the bottom one would represent our oxidation half reaction, where the electrons are a product. Next step, make our electrons gained equal our electrons lost, multiply everything in the top one through by 3, multiply everything in the bottom one through by 2. Rewriting our 2 half reactions, we're going to have 6 electrons plus 3 ClO minus plus 6H plus, and on the product side we're going to have 3 Cl minus plus 3 H2O. For our second half reaction, we're going to have 2 CrOH4 minus, and on the product side, 2 CrO4 2 minus plus 8 H plus our 6 electrons that need to cancel. Adding together our half reactions, we have 6 electrons on the right and the left hand side that will cancel each other out. We also have some hydrogen ions that we can reduce down. All 6 of our hydrogen ions on the left hand side will cancel with some of the 8 that are on the right hand side. We'll be left with 8 minus 6, or 2 hydrogen ions on the product side. When we write out our equation, we're going to have 3 ClO minus plus 2 CrOH4 minus, and on our product side, we'll have 3 Cl minus plus 3 H2O plus 2 CrO4 2 minus plus 2H plus. This is where we would stop if we were balancing an acidic solution. But since we're not balancing an acidic solution, we're going to have to add our additional steps in. Our next step is to look at the number of hydrogen ions and add the appropriate number of hydroxide ions. Notice on the right-hand side we have 2 hydrogen ions, so that means we're going to add 2 OH minus to the right-hand side, and what we do to the right we also have to do to the left. So we're going to come over to the left and also add 2 hydroxide ions. Hydrogen ion plus hydroxide ion gives us water, so the combination of those is simply 2H2O. Also notice we can combine like terms. We have 3H2O right here that we can combine on the right-hand side with our 2 waters that we just formed. That'll give us our final balanced equation in basic solution. We're going to have 2 OH minus plus 3 ClO minus plus 2 CrOH4 with a -1 charge On our product side, we'll have 3 chloride ions plus 5 H2O when we add together our 3 and our 2 waters, plus 2 CrO4 2 minus. When we have a basic solution, the things you're looking for are being left with hydroxide ions and often being left with water. But definitely not being left with hydrogen ions, since that would signify you balanced it in an acidic solution. Let's try our last example, balancing once again in basic solution. It's good practice to balance in basic solution because you're following all the steps for balancing an acidic solution, but just tacking on those few steps at the very end. Our 2 half reactions are going to be zinc going to zinc 2 plus ion, and our nitrate NO3 minus going to NH3. Checking out our first half reaction, we have 1 zinc on the left, 1 zinc on the right. So everything's balanced by mass. Going to balance by mass on our second half reaction, we have 1 nitrogen on the left, 1 nitrogen on the right. We have 3 oxygens on the left and none on the right, so we're going to need to add plus 3 H2O. And now we have 3 times 2 are 6, plus 3 more. We have 9 hydrogens on the right, so we're going to need to add 9 H plus to the left-hand side. Now everything is balanced by mass. Balancing by charge, our zinc on the left has no charge. Our zinc on the right has a plus 2, so we can add 2 electrons to the right-hand side to show our oxidation. And for our second half reaction, we have 9 hydrogens and 1 nitrate. Our total charge is going to be plus 8. And on the right-hand side, we have ammonia, which has no charge, and we have water, which has no charge. So we have 0 charge on the right-hand side. In order to make our 8 a 0, we're going to have to add 8 electrons to the reactant side. Next, we'll make our electrons gained equal our electrons lost. If we multiply just the top reaction through by 4, we can make our 2 electrons equal 8. We would have 4 Zn going to 4 Zn2 plus 8 electrons as a product. Let's rewrite our other half reaction. 8 electrons plus 9H plus NO3 minus going to NH3 plus 3H2O. Now we can add together our 2 half reactions. Our 8 electrons should cancel, and our overall reaction so far will be our balanced equation if we were trying to balance an acidic solution. So 4 zinc plus 9H plus NO3 minus going to 4 Zn2 plus NH3 plus 3H2O. Now we want to determine how many hydroxides we need to add. We have 9 hydrogen ions on the left, so that tells us we need to add 9 hydroxide ions to both sides. So 9 hydroxide on the left and 9 hydroxide ions on the right. Our 9 hydroxides combine with our 9 hydrogens to form 9H2O. So we get 9 water molecules from the combination of the hydrogen and the hydroxide. And we can simplify further. We have 9 water molecules on the left, and we have 3 water molecules on the right. All 3 of those water molecules will cancel, and we'll have 9 minus 3, or 6 H2O left over on the left-hand side. So writing out our full balanced equation in basic solution, we've got 4 Zn plus 6 H2O plus NO3 minus going to 4 Zn2 plus NH3 plus 9 OH minus. We check and we have water and hydroxide left, which tells us we were in a basic solution.